looking at the 2021 US Open Gold question number 2. And so in this question, we're going to have various vertexes, each one with 4 portals. And so these 4 portals are only going to be able to be traveled in a certain way, unless we pay C moonies depending on the vertex. And so what we're going to do is we want to modify all of the vertexes, or some of them, in order to reach every possible location. And so we're going to get the minimum total amount of moonies that we need in order to solve this question. So let's go look at the algorithm for this question. So the main thing we're going to actually notice about this question is that even though it is a graph question, what we're actually going to do is we're not going to create a graph using vertexes. We're going to create a graph using portals. And so if we were creating something where every vertex had a bunch of edges that were portals, it would be a lot harder of a question. But instead, what we're going to do is we're actually going to create a graph where every node is a portal. And so what this means is when we look at the input, what we're actually going to do is we're going to use the portals to build a graph. And so what we're actually going to do is we're going to create from every portal 2 connections. It's going to have 2 edges. And we're going to assume that we don't have any switching going on. This is just assuming all of the vertexes are locked in place. The portals can only go to their respective other portal. And so what this means is that between 1 and 4 there would be an edge, between 8 and 9, 1 and 2, 5 and 6, and so on. And so we're going to assume there's no switching involved. And what we're actually going to do is we're going to go from 1 and 4, create a line, and the other line is going to be from one side of the portal to the other side of the portal. And so what we're going to do is we're going to actually, after doing a couple test cases, find out that these paths are actually going to end up in a cycle. And what this means is if I were to have a fully connected graph, like the question wants us to, then we would have a fully connected cycle. But what we're actually going to discover is if we use the portals as nodes and the connections between portals as edges, we're going to have multiple cycles. So if we follow this, let's say we start at portal 1, we go to 4, we go from 4 down here to 3, 3 to here, to 2, 2 to here, back to 1, 1 to 1. We're actually going to find out that this right here is going to be a full cycle. And so if we're going to look at the other parts, let's say I start at portal 8, 8 goes to 9, 8 goes to 8, 10. We're actually going to find out that this is a second cycle. And we can use the remaining nodes and make a third cycle. And so what this is actually going to do is, depending on the portals, we're going to basically be able to have our nodes, and we're going to be able to create multiple cycles. And so the second main observation we're going to make is going to be regarding these cycles. So let's assume that because we have edges between 1 and 2 and 3 and 4, we know that portals 1 and 2 are going to be a part of the same cycle, and portals 3 and 4 are going to be a part of the same cycle. So if you look down the list, 1 and 2 are going to be part of the same cycle, 3 and 4 are going to be part of the same cycle, because they have edges connected to each other. And so what we can actually note is if we have a vertex, so in this case a full line, where we have 2 cycles, and in this case that would mean 1 and 2 are part of, say, cycle red, 3 and 4 are part of cycle blue. What we can actually do for this question is, in order to, say, finish the question, we need to have all of the portals in one big cycle. And so what we're actually going to do is we're going to need to merge these 2 cycles into one. And we can do this by noticing that if I pay the amount that this vertex needs, I would be able to switch the connections around. And the important part of this is, since we know that from here, there's a loop leading back to here, we know that if we get rid of this edge, these 2 points are still going to be connected. And likewise, since we know that there's going to be a loop going around here, then we can also get rid of this edge. And so what this means is that if we pay the price of this current vertex, we can combine these 2. So we combine it like this. And we'd be able to pay and connect these two cycles. So by connecting these two cycles, we only had to pay the amount for the vertex. And so what we can actually note here is that the combination, or the way that we change the way they're connected, doesn't matter. So there are only two ways we can do this. If we do it where it's the outer one and the inner one, like here, you can see they're connected. And if we did the other method, or we did say here and here, if you follow this path, it's still connected. So all we have to do is we can ignore everything, and we can just note, in order to connect two cycles, where they have one part here and one part here, both at the same vertex, so if these two cycles share the same vertex, all we have to do is pay the vertex cost, and then we're able to connect them. And so knowing this, what we can actually do is we can transform our question into something different. We're going to actually transform it into something harder, into a Kruskal's MST algorithm. And so what we can actually do is we can look at these cycles, and for every cycle, we're just going to record the vertexes it goes through. So for this dark blue cycle here, it goes through vertex 1, it goes through vertex 2, 3, and 4. And then for this red cycle over here, we can follow its path. So for this red cycle, it goes through vertex 1, it goes through vertex 3, and 5. And then for the light blue, it's going to go through 2, 4, and 5. And so what we can actually do is we're going to transform this question into combining these cycles, where every cycle is going to be a node, and we're going to combine them together based on whether or not they share the same vertex, because if they share the same vertex, we can combine the two cycles right here. And so if they share the same vertex, we can combine the two cycles. And so what we're actually going to do is we're going to basically turn this into Kruskal's. So we're going to use a greedy algorithm, and we're going to find the smallest weighted edge, let's say in this case 4, and then you can see 4 is a part of this group and also this group, which means we can combine these two cycles for a cost of 3. So this would make our nodes look like 1, 2, and notice that the order that the cycle goes in, so in this case the order, if we follow from 1, would actually go from vertex 1 to vertex 4 to vertex 3, but basically the order doesn't matter, and all we have to do is we have to know which vertexes are in every cycle. So what this basically means is, because these two vertexes share 4 in common, we can basically just use like a set and then combine these two together. So when we combine those two, it would be 1, 2, 3, 4, 5. And then the other one is 1, 3, 5. And so this has a cost of 3. And then for the second one, we're going to find the second one with the second lowest cost. That's going to be 1. And so we're going to look at vertex 1. We're going to find that it's in both nodes. We can combine them together. And then we have a total cost of our answer 13. And so overall for this algorithm, what we're basically going to do is we're going to create a graph using portals and not vertexes, so that we are able to create cycles. And you can tell that they're cycles because from every node, or from every portal, you're only going to have 2 different edges. And you're going to have one leading to the one next to it, and one leading to itself. So what this is actually going to look like is it's going to look like a chain of connected nodes that's definitely going to lead back to itself. And this is mostly because for every node, you only have 2 edges, so it's going to lead back to its original. So we won't have scenarios like this because we cannot have this 3-way intersection. But basically what we're going to do is we're going to create this graph, we're going to find the cycles, and then for every cycle, we're going to record which vertexes it goes through. And for each of these, what we're going to do is we're going to use the property here where we can combine 2 cycles if they have a vertex in common. And then we're going to use the Kruskal's algorithm in order to basically combine these at the lowest possible cost. So let's go look at the code for this question. So I've gone ahead right here and I've basically defined a couple of data structures. And so the next thing we're going to do is we're going to read in our input. So I'm going to resize cost, and I'm going to call a function called make. And make is just basically going to resize everything and set it up. So I'm going to resize a bunch of my things. I'm going to use iota, which is basically going to fill parent with all of the values from 0 to the size. So parent 1 is going to be equal to 1, parent 2 is going to be equal to 2, and so on and so forth. Over here, I'm just going to use a fancy way to basically set neighbors 0 or neighbors 1, depending on the loop, and it's going to set either neighbors P1 to P2 or neighbors P2 to P1. And then the same thing here, neighbors P3 to P4 or P4 to P3. And then what I'm going to do is I'm actually going to sort my cost. So it's important that we sort costs from least to greatest. And then what I'm going to do is I'm going to call a function called runP. And so what this is going to do is it's basically going to do a DFS, and it's pretty similar to flood fill. We're just going to flood fill, and it's going to return the number of groups that we have. So I have runP here. And so what it's basically going to do is we're going to have G be the number of groups. We're going to loop through all of the nodes, and because we're using portals as nodes, we're going to need 2 times the amount, because every portal is going to have 2 different values, and we're going to check if it's visited. If not, we're going to DFS. And so when we DFS, it's pretty standard. We're going to check if it's visited. If the node is visited, we return. If not, mark it as visited, go through its neighbors, and then we're going to DFS until we find our cycle. So once we found our cycle, what we're going to do is we're going to set up our union find. And for our crucicles or our union find, what we're actually going to do is we're going to set our start. And right here, what this is going to do is it's going to find the first value, so make start, which is going to loop through the nodes. And so nodes is going to be, when we do our DFS, it's going to be a public set that we clear every time. And so it's going to contain all of the vertexes that we've visited while doing our DFS. So what make start is just going to do is it's going to make start the nodes.begin, so the first vertex that we found. And then what we're going to do is we're going to actually use something called shift over. And so what we're going to do is, because we have 2 portals, so we're going to have 2 identical portals, we're actually going to shift one over. And so what this means is the first occurring value is going to be itself. So let's say the first occurring value of portal 1, it's just going to be 1. But the second occurrence of portal 1 is going to actually be a shifted version. And so to convert it, we're going to use shift over. And so what it's going to do is it's just going to shift it over 2000 using shift. And so this is just to make sure we don't have any collisions and that every node is unique. So we're going to shift over, it's just going to return a plus shift. And then what it's going to do is it's going to check found. And so what found is going to do is down here, we're just going to add 1 to found every time that we use a node. And so what this basically means is if I have portal 1 and it appears the first time, found is just going to be equal to 0. So we're going to assume that it's still nodes.begin. And if found is greater than 0, which means it's already appeared once, we're just going to shift it over once. So we're going to have found previous, we're going to add 1. And so what this is basically going to do is we're basically going to update found for the next value. And then we're just going to return start. So this was a long way of basically being able to find the first value. And then we're going to loop through the rest of the nodes, or actually vertexes. And when we loop through these vertexes, what we're going to do is we're going to run join. And what run join is going to do is it's just going to join the 2. And so when we join, this is going to be a union find. So when we had those circle groups earlier, what it's basically going to do is it's just going to join all of the circle groups so that we have the vertexes all joined together into separate groups. And then when we do our union find, we're just going to merge those groups. So for the union find code, what we're actually going to do is we're going to have 2 main functions. We're going to have getRoot and we're going to have join. So for my join function, it's actually a bit optimized. I haven't tried it yet, but I'm pretty sure you could just get away with a typical join. But what I've basically done here is I've used an optimization. Otherwise, you can just use a standard crucibles, or actually union find, join, and then find root or get root. So I have these two functions here, and then I'm just going to run join, which is going to join either start in the shifted version of val, so like the second occurrence, or start in the first version of val. And so after I've joined them together, I'm going to add 1 to found, and then move along j. And at the very end, I'm just going to clear nodes and add 1 to group. And so this is going to loop, and it's going to run, and I'm going to return the total amount of groups that we have. And so over here, I have num of groups as run p. And then what I'm going to do is I'm going to have our answer as union find num of groups. And so what this is I'm going to have my function here. The algorithm is technically crucibles. And what I'm going to do is I'm going to loop through, and while my index is less than cost.size, so basically while I still have vertexes and I still have more than one group, I'm going to find the smallest value. So I'm going to find the cost ind.second, which is going to give me the vertex that this cost is. I'm going to check here, and what this is actually going to do is, in the case where I have a scenario where I have a vertex where I have 4 dots, and these 2 are part of a group, and these 2 are part of a group or cycle, and these 4 are all part of the same cycle, what this basically means is that found val is only going to appear once. And this is a slight optimization, but what it means is, since I used a set up here, if a vertex appears multiple times in the same cycle, it's only going to appear once. And so if that vertex appears twice or multiple times in one cycle, that means it's not going to appear in any other cycles. So this is basically an optimization. You can completely ignore it. But what this is going to do is it's just going to check if both sides of this current vertex are in the same cycle, then I'm obviously not going to be able to use it to basically merge 2 cycles. So what I'm going to do instead is I'm just going to continue. And then over here, I'm basically going to join the 2 cycles, subtract 1 from number of groups. I'm going to add the cost. And at the very end, I'm just going to return my answer. And over here, I'm going to print it out. And that's the end of our program.